Well, welcome back. Nice, brisk, cold, gray morning. In fact, this is a picture of the weather outside. No, it's not. It's supposed to be my slide. Can you put up the overhead or the projector from the... There we go. Good. No, it's there but not... It's moving. Okay. So, solving a triangular... There we go. Solving a triangular system. Lx equals b. Okay, we left off with this idea that there's something with the... All right. Here we go. Great. We left off with these two rules, these implications. Okay? If bi is non-zero, then xi is non-zero. If xj is non-zero and there's an I such that lij is non-zero, then xi is non-zero. Okay, so this gives us a way, if we have a graph of L that looks like this, say, and it can't be, it's acyclic, okay, the matrix L is already a graph representation of this graph, right? Because what you need to look at is if we're creating thinking of an adjacency graph where this is the out adjacency of node J is this column. So there's the I, and that means there's an edge from node J to node I in the graph. So we have already a very natural, already an explicit representation of the graph that's all ready for us to use. And then if, for example, this non-zero, this is a non-zero in B, and if, say, this is a non-zero in B, then all we've got to do is start at these positions and then find that, okay, well, if this is non-zero in X, there's an edge from here to here, so that's non-zero in X. And if this is not a non-zero, it corresponds to a non-zero in X, this node, well then, so is this one, and also through this one, and this one, and this one. So we just have to do a graph traversal, starting from the nodes in B, asking what nodes can we reach. That gives the non-zeros in X. Now there's something else really intriguing about this graph traversal. Okay, a graph traversal takes time proportional to the number of nodes you have to visit plus the number of edges you traverse. You don't traverse all the edges of the graph necessarily. So the question is, which edges get traversed? That edge gets traversed in unit time. Well, whatever constant time is. But what does this edge represent? What is the edge? I mean, think about this rule. We've got J and I. This edge from J to I represents a value in L which I must use in my numerical computations. It's this rule right here. But this rule right here came from this numerical statement where I've got two flops to perform. So in the graph traversal, to find the pattern of X, I visit an edge. And I take time proportional to the number of edges I visit. For every edge you visit here, you do two floating point work here. So there's a one-to-one correspondence between the two. So asymptotically, it's the same. This is order flops. To compute the graph traversal takes time order flop count. Plus the number of non-zeros in X. Okay, because those are every node we have to visit takes a unit time. But if we assume, here, for instance, that a node in X, if it's visited where b is 0, that means we did work to get to that node, numerical work, so we could attribute the work to that. And remember this number of non-zeros in B, if we assume that the diagonal is non-unit, then we have a flop to do for every value here as well. So this goes away. And this is also the time complexity for the graph traversal. Okay, the nodes in B and X. So the whole thing then becomes, if we make that simplifying assumption that, yeah, we have work to do for every non-zero in X, at least, constant work to divide them by the diagonal, then this just goes away, and it's dominated now by F. So we have order flops here, order flops there, and we don't spend more time to figure out what to do than actually doing it, which of course would be bad if we did that. And the total algorithm takes time proportional to the flop count. Well, you have to do the flops. So any algorithm, no matter what you did, would take omega flop count. And we just have a big O flop count. So it's theta flop count. It's a tight asymptotic bound. We do precisely the amount of work we need to do. It's an asymptotically perfect algorithm. Can't get any better than this. Asymptotically. Okay. I should add, when you do backslash in MATLAB, it doesn't use this method. It uses a method that's not asymptotically perfect, but it's 10 times faster. That's another story. That's the multifrontal methods, which I'll talk about later. So now, and this just gives us a picture here of the two rules. We have the one rule that says if Bj, or actually I have a J here, if Bj is non-zero, then Xj is non-zero. And if Xj is non-zero and there's an Lij that's non-zero, then Xi is non-zero. So these two rules together then give us the set up for us the problem of doing the reach. So how do you compute the reach? Well, you can compute it in lots of different ways there's many different ways of traversing a graph, right? But what I'm going to do here is use a depth-first search, and there's a reason for that. Think of the innermost loop. Think of the numerical dependencies, I should say. That statement is all the flops we have to do in that statement. I'm assuming the diagonal is a unit, so I don't have to divide by the diagonal. So that's noise. We could consider that if we wanted to, but that just doesn't change the whole the problem. Okay. Subtraction is associative and commutative and all that. I can do it in any order. But I have to have, so X starts out as B. I can do that at the beginning. All right. And then as I compute, I can subtract values from Xi in any order I choose, as long as I multiply Lij by the right value of Xj. So in other words, I must have finished the computation for Xj before I use Xi for its subsequent updates of further nodes and further columns in the graph, right? So you have to compute Xj before before you can use Xi to compute do its computations. Well, what does that picture of that data dependency look like? Here's an Xj. Okay, I have to compute this before I can use Xi to update its peers. Okay, every edge here represents a numerical computation of taking Xi, multiplying it by this entry in L, and adding it to there. So the graph captures the data dependencies as well. It does not only capture where the non-zeros are, it captures the data dependencies. You've got to do this first, and when you finish this, you can do this. And when you finish all the work here, all the different updates, so this is being updated by many different other values of X. But once you've finished all of these updates, this guy is done, and then you can do these. So this graph gives us the data dependencies. I have to do this before I do that. So now the question becomes, well, what order do you visit the nodes? And we have this list of, suppose you do this graph traversal. You get the list of nodes in X, calligraphic X, right here. Suppose you compute that. Okay. Well, fine, you have it, but then you've got to go back here and make sure you satisfy all the dependencies. You've got to make sure you do the numerical work here before you do the numerical work here. Here being, thank you, yes. Do the numerical work on this node before you do that. So there's two things. There's one, knowing what nodes to compute and doing them in the right order. Well, because the graph is acyclic and small nodes come before big nodes, we could just do it in the natural order. We could compute X, the non-zero pattern, and then just sort it from 1 to n, from small to big. We could do that. And then we can just do it in that order. And that'll satisfy all these dependencies because j will be always less than I here in this picture. But if we did that, we break the asymptotic efficiency. If we do that, if we did the sort, I would add an extra logarithmic factor. If I put the size here. Okay, and this may dominate our flop count. The flops could be proportional to the number of non-zeros in X, not logarithmically increased. So I can't sort. This is too expensive. So I need some way of producing an ordering of X that satisfies the dependencies. Well, there's a name for this. It's called a topological ordering. A topological ordering of a directed acyclic graph says order the nodes of the graph, from say left to right, so that all the edges go from left to right. So that means here, for example, I could number this first, and maybe this second, and this third, but this has to come fourth, and then I could number these in any order. I could number these in any order. It doesn't matter what order I put them in. First, second, third, whatever. This one has to come fourth because it's got to come after these three and before these four. But you see, there's a lot of flexibility in how these nodes are ordered. I don't have to sort them. All I need is a topological order. The beauty of a depth first search as opposed to a breadth first search is that a byproduct of the depth first search is that it produces the nodes in topological order. That's the beauty of it. And I'll show you some examples in a minute. So here's a depth first search. You've seen a DFS before, I assume. If not, go back and freshen up your algorithms knowledge. But it's a very straightforward algorithm to write recursively. Its recursion, though, is going to be a problem we'll have to avoid because the stack depth can be size n, and n can be 1,000,000, and that can cause stack overflow on any given machine. So we have to do our own recursion. But anyway, let's delay that point. Here's a complete specification of a depth first search. So the outermost loop just has to walk over all the nodes in B. And if it's not marked, do a DFS. So you look at the nodes, and you have this entire graph, and just one at a time, you start at a node in B, and you say, okay, do a DFS here, do a depth first search here, do a DFS, and do a DFS here. Okay. And it doesn't matter what order I visit these nodes in. I'll still produce a topological sort of the graph. So to do a DFS, you just mark the node, because you only start the DFS if it's unmarked. You mark the node, and then for every outgoing edge that's not marked, you start a DFS. And then when you're done as a post-ordering, after you've done the DFS of all your children here, you push yourself on a stack for the non-zero pattern of the result. So this is a global variable, if you will, that exists between all layers of this recursion. That's a complete DFS. So let's see how this works on an example. No, this is not what I want. I want this picture. Here we go. So let's suppose that B4 and B6 are non-zero. Then if you look at the DFS at, say, suppose we start with node 4. We could start with node 6 and we'll still get a topological order. If I start at node 4, then I'll immediately start and so let's see, how do I want to write this? I want a bracketing kind of layer. So this is going to be 4. So I start a DFS on 4, and the finish of it is going to be down here. So when I start 4, I first start 9. So I go from 4 to 9. But when I start at 9, so 4 is still pending, 9 starts. Now 9 is going to go from 12 to 13. Which one do you want me to do first? I don't care. 12. Okay. So I'm going to start 12. From 12, I'm going to then start 13. Now I've got 4 layers of recursion going on here. And from 13, I will see 14. 14 will start and finish. And I'm going to put 14 now on the stack at the bottom. So 13 comes back and asks, are there any other neighbors? No. So it finishes. So 13 gets put on the stack. And so I come back here, 13 finishes, and then 12 returns, and 12 says, does anybody else come on the stack? And the answer is no. So 12 finishes. So 12 goes on the stack. And then this is kind of a boring recursion here. 9 finishes because 13 is marked. I mean, 9 looked at 12 and said, okay, we started it. But then when we come back and 9 looks at 13, 13's already marked, so we don't do it. So 9 goes here on the stack, and then 4 finishes. So we have 4 on the stack. But we're not done. I have to iterate across the next node 6. So I start at 6. And I visit, let's make this, well, doesn't much matter. I look at 9 and I do nothing because it's already marked. I look at 10 and I'll start a DFS. From 10, if I look at 14 now, or 13 or 14, I'll do nothing because these are already marked. From 10, I'll look at 11, though, and see that, oh, I've got work to do. So I'll start 11. 11 has no unmarked neighbors. I'll look at them, 12 and 13. In other words, I'm spending constant time here from node 11 to look at node 12. So there's work to be done on this edge. I look there, but then I don't, do anything. I look here, and then do nothing in addition to that. So I start 11 and finish it, and so 11 gets put on the stack, and then 10 gets put on the stack, and then, whoops, was 10? Yeah. 10 gets put on the stack. 9 was not started, so it doesn't get put on the stack, and then 6 is. So there's my DFS. There's my output stack. 6, 10, 11, 4, 9, 12, 13. And it's out of strict lexicographical order. And I could spend an extra x log x time to sort it, but I can't afford that because this would break the asymptotic, the x log x would break the asymptotic time complexity of the algorithm. But look at this. If you were to go back now and write all the edges, okay, let's draw them. 6, see, we've got to do, for example, the computation on node 6 before we start the computation on node 9 because of that edge. That edge represents a data dependence that looks like this. Okay, so I've got to finish the computation for 6 before I can use it to update 9. So 6 has to be computed before 9. So there's an edge from 6 to 9 in the data dependencies. There's also an edge from 6 to 10. So what about nodes 10? What's the outgoing edges for 10? 11 and 14. 11 is here, and 14 is there. From node 4, 4 has an edge, outgoing edge to 9, nobody else. 9 has outgoing edges to 12 and to 13. And 12 has an outgoing edge to 13. And 13 has an outgoing edge to 14. It's all downhill. Right? So if I compute, if I do the work, this outermost loop, so I've got my algorithm goes x equals b for j, for each j in x, do, and then for each I in the non-zero pattern, do xi minus x equals xi minus lij xj. Okay, so this j, if this j iteration goes this way, then all the data dependencies, if I start for this j loop right here, is going to go not in order, strict order, it's going to go in topological order. It'll go 6, 10, 11, 4, 9, 12, 13, 14, but it satisfies all the data dependencies. So the results are not being computed in what you would think is the natural order. But finding that natural order is too expensive. The topological order suffices, and the beauty is it's a byproduct of the DFS, which I needed to do anyway to find the non-zero pattern, and the DFS takes time proportional to the flop count. So click, it all just meshes together. You see that? Isn't that beautiful? This is just a beautiful algorithm. I can say that because I didn't invent it. Invented by a co-author of mine, John Gilbert. Before this algorithm, all sparse factorization methods, there were none that were asymptotically perfect. There were none that could provably take time, always take time proportional to the flop count. Which seems like a trivial request. How much work does your algorithm take? Whatever it needs to take. Every flop has to be done. Seems like a reasonable request, right? But you see, with a sparse matrix algorithm, you can spend more time monkeying about with your data structures. You can spend more time figuring out what to do than actually doing it. It's very easy to do that. All right, think about project 2 that you're working on right now. You're doing all these dot products between pairs of columns. And I assume you've started looking at it, right? Now, if that was the method of choice for doing matrix-matrix multiply, you'd be toast. It would not be a good method because imagine just doing a single dot product of two very long vectors. What if the non-zeros between these two vectors don't line up at all? Okay, what's that? You've wasted time, right. You've spent all this time figuring out that you've got nothing to do. So the work is not order flop count. To do a single dot product of two sparse column vectors, the work is time proportional to the data structures, at best. You've got to go through everything to see that they don't line up. Now, we can't do any better than that because you've got to visit, I don't know of any way of doing better than that. Because you've got to somehow probably visit every item in your data structure. Okay. To see if there's an overlap, at least for that problem. I don't see a way of getting around it for the sparse dot product. They don't line up. So you zero work and you spend time proportional to the length, the number of non-zeros in each of these two vectors. And it doesn't appear to be anything around that. And so what that means is if you base a larger algorithm upon sparse dot products, your algorithm will not be time proportional to flop count. Period. So it's a very hard thing to do. I mean, dot products appear all the time in numerical algorithms, but you can't use them if you want, in this case, if you want perfect asymptotic time complexity. This algorithm is also intriguing in that it's in a sense like binary search, right? Binary search, so forget this problem for the moment. Think about binary search. You've got a sorted list of numbers. You want to know is the number 5 in the list, whatever. You go binary search and you know it's sorted. So you go bing, 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 and you find it in logarithmic time, right? Time, it's log of the size of your data set. And the reason it's not the size of your data set is because you know you don't have to visit all the data. You have a problem size n you solve in logarithmic time. The only way that can work is if you don't touch all the data. Okay. This is like that. We have a graph traversal here. This graph right here, or this graph over here on the slide. This graph could have 1 million nodes in it. I mean, I didn't touch this part of the graph at all. There are 4 nodes here. There could be 4 million nodes here. I still take that amount of time. Whatever time it takes to do the flop count, do the flops. I mean, presumably sometime in the calculations of what you're doing, you had to set this problem up to begin with. So you created the graph of L. You computed L at some point. Okay. But now that you've got it, you don't want to, every time you do something to this graph, touch the whole graph. Just like with binary search. At some point, you had to sort the data, right? Does that mean binary search? Oh, that's useless. Binary search is useless because you had to have computed and sorted the data in the first place. So why do you care about binary search? Just look through all the numbers. Well, but that's not how we use a dictionary, is it? Somebody sorted the dictionary once. Every time you look a word up in the dictionary, do you start at the first page looking? If I wanted to look up the word random in the dictionary, do you start at the first page? Aardvark. No, that's not random. Apple. Well, Apple doesn't. What would be the word abacus? I don't know. What comes after aardvark? No, that's not the word random. Obviously you don't do a linear time search. Well, but it took you more than linear time to create the dictionary. Well, somebody else did that. They've already done it. The same thing here. The graph is already there. Okay, somebody already paid the cost to compute it. Now I just want to quickly traverse it. The cool thing is, though, is when we get to which chapter? I forget. You'll see that, in fact, I'm going to use the triangular solve to compute the graph in the first place. Okay? Pieces of it. It's going to be built piece at a time. And if every time I did the depth first search or did the triangular solve, I spent time looking at the entire graph, then I can't compute this efficiently. All right. It turns out that LU factorization can be recast as a set of n lower triangular solves. Each solve is computing a new column of L. Every column of L can be computed by a triangular solve. So to do an LU factorization, I've got to do this n times. So if each of them took order n time, it'd be n squared total, which would stink. It would be awful, right? I mean, think of it. You give me a tridiagonal system. We know that we can factor it in order n time easily. But you give it to an algorithm that's not asymptotically efficient, it could take n squared time. That's not a sparse matrix algorithm anymore. N squared is not sparse. N squared is verboten. Except for project 2. Because here n is, in project 2 you're making the assumption that n is small. But there's another dimension that's big. But you're taking n squared plus the flop count time, or plus something else. Your n is small. You're assuming that, right? Because you're assuming in this matrix multiplication, A transpose B, or if A is stored in sparse row form, you're assuming that M and N are very small compared to K. So your time complexity will be order Mn plus something else. Okay, that's not order K. It's order flops or order number of non-zeros, whatever. Actually, what this B is not trivial. But this is dominant over the M and N, even the product, if this is very tiny. So this is it's a niche algorithm. It's an algorithm that has to make, in order for it to work efficiently, it's got to make some key assumptions about its input. And you would not attempt to use this on any matrix, just when that occurs. But the cool thing is that this often happens. And for Project 2. And I wrote the code for the MathWorks to do this, but they don't exploit it just yet because I don't know, they haven't plugged it in fully yet. But it has to be able to do the following. You have to be able to look at this and treat this as a combined operator. And then notice that, okay, how are we going to multiply A transpose times B? Then you have to make a choice. Do I transpose A and then multiply by B, or do I use the sparse dot products? And the choice should be made based on the sizes of the matrices involved, so that you pick the algorithm that you think will be fastest or take the less memory. So anyway, that's whoops. So now let's look at the mechanics. So do you see the details, or do you see the big picture? I hope. If you don't, please stop. I mean, because you got to see where I'm coming from. You have to understand this theorem for what I'm about to say next. I mean, if there's something in here that's not clear theoretically, then the rest of my discussion is pointless. Does it seem pretty clear? Okay, you've got the core thing is the DFS, and the basic idea for that is that it produces the topological order. And then the DFS comes about, because of this picture here, those rules, those two logical rules right there. Those two rules give us that theorem. Those two rules come from the algorithm. So the algorithm gives us the rules gives us the theorem, and then we just need to do a DFS to find out where the non-zeros are. Okay, so now, having said that, we still want to write code for this, which is efficient. And we can't do a recursive DFS, unfortunately. The problem is the stack depth of a depth-first search can be order n. In this case, n could be a trillion, a million, a billion, or whatever. It could be enormous. And every time you call a function, you push on it not just data, but also things like where to return, your return address and all this stuff. So you've got all this stuff stuck on the stack, okay? And most systems that support recursion, think of, say, quicksort. The depth of quicksort recursion is only logarithmic, not order n. So doing a recursive quicksort is not a problem. But if your operating system has space for the call return stack that's not order n in size, then you'll have stack overflow, and your program the operating system will just crash, just terminate your program. And in fact, there was a bug in MATLAB, which I fixed. There was we'll look at it when we look at chapter 7 or 8 on ordering methods. But there's a thing called DMPerm, domain-Mendelssohn permutation, which finds this block triangular form. It requires, the gist of it is, it requires something like a depth-first search. And the natural way to do that is with recursion. The algorithm originally in MATLAB was recursive. Okay. The stack depth rarely reached order n. But the problem is, as matrices grew in size, and for particular matrices, the stack depth could be very large, stack overflow occurred. And when stack overflow occurs, it's actually worse than a seg fault. You get these, in MATLAB, with Project 1, right? You get these big voluminous, okay, stack traces and this is a problem, blah, 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 blah. Do you wish to terminate MATLAB? Okay. Oh, yeah, I'll better terminate MATLAB. You've seen those, right? Stack Overflow is worse than that. With a Stack Overflow, you don't get anything. You don't get any dialogue that says, do you want to continue? It's gone. Your window just goes, disappears entirely. And if you were running at MATLAB-Node desktop, you used to get core dumped or something. What's the word? I think not core. There's a word for it. There's a single line that comes out of the Linux command, and you don't get any stack trace or anything because the stack is corrupted. It can't give you a stack trace because the stack is overflowed. So the operating system just says, well, I can't do anything. Terminates the program entirely. So Stack Overflow is the worst of bugs. So it's very insidious. So we can't. So this, if I implemented this recursively with this, okay, on the slide, it would fail for large problems. But it's a beautiful little algorithm. Okay, compare the two. You can do this. You've got your book in front of you. Here's the pseudocode. Here's the C code. And there's a one-to-one correspondence. It's very, and I wrote this with a few assumptions. Okay, let me show you what the assumptions are. I assume I've got a workspace of size n called W that I start with. And basically, this is traversing through a sparse column vector, B. And it gets a row index, B of I, of P. And it says, if it's not marked, then do a DFS on that, starting at that node. And the output stack is held in the array xi. So xi minus minus top equals j does the push. One line statement in C for doing a push. So here I visit, I'm at node j. I mark node j, because I'm not visiting it unless it's already unmarked. I mark it by setting wj to 1. I traverse all my neighbors. I ask, oh, if you're not marked, do a DFS starting at that node I. So there you go. I mean, and you see the comments here just mimic the pseudocode. Very simple algorithm. If we used this, and suppose recursion was okay. If we use this, we would have to worry about the fact that W is initially all 0, and then some of it, as you go, gets set to 1. So now when the algorithm finishes, it's got this W vector, some are 0s and some are 1, which are on output would be fine if you want to throw it away, but wait a minute. How does it start out to be all 0? We can't spend order n time setting this whole vector to 0. Okay, so we have to make an assumption. We have to assume that we have a vector lying around for free that's already initialized to 0. But then if I make that assumption, I better, if I think of a loop invariant or something where it says, okay, at this point in the code, I know that W is all 0. Well, if you go and mangle it up and mess it up, now it's 1s and 0s, you can't go back to that assumption any longer, even if you started with that assumption. So if I make that assumption at the beginning, then I have to clean up and get myself back to that state when I'm done. But that's not hard. I could do that. So I could start with a vector of all 0s and imagine the time has been paid already to build that vector of all 0s of size n, the W vector. When I'm done then, all I have got to do is iterate through the stack here. I could do it here, for example. Here's the stack xi. I could just iterate through this and set W6 to 0, W10 to 0, 11, 4, 9, 12, 13, 14. Set them all back to 0, and then we're back to where we began. Because no other entries in the graph were marked. No other nodes were marked, so all the other W values, the marked values of those are 0. They're unmarked. So that would clean up after ourselves when we're done. And there's a lot of sparse code that will do that. It'll start with an assumption, okay, I've got order n workspace that has some state that I can assert is true for every entry in this array without spending the time to make that happen. You do some work, you do some work, you touch part of this array, you do some work, you do some work, you touch some more of it, and then you clean up by patching up the stuff you used. Not by going through the whole array and sending it all to 0. That will kill your asymptotic time complexity. And if you do that, you'll see red marks all over your project, right? You can't do that. You have to be very careful about where order n loops are the bane of sparse matrix algorithms, and they are insidious. They're insidious. They creep in almost without thinking about it. You have to be steel-minded to avoid them. It's very common to write asymptotically incorrect code by putting in an order n loop here, an order n loop there, and then you're dead. You don't have a sparse algorithm anymore. Forget it. So anyway, so the W array is not a problem. We could get around that by making the assumption at the beginning and then going back, fixing that assumption when we're back. Okay. But there are other ways of handling this marked vector that I've already alluded to, which are actually better. We can make this cleanup work take constant time. Okay? If I'm going to reuse this vector over and over again, I could start with a vector, say that's all 0. And the first time I use this vector, and I'll keep another scalar with this vector that says all the entries in the vector are less than, say, 1. Okay, so I start with a vector of size n, and I have a scalar, and it's equal to 1. And I start with the assumption that everything in this vector is less than 1. It's 0, say, or negative, whatever. Then to mark a node, I set it equal to this value, this marked value, which in here is hard-coded to 1. Okay, but fine. The next time I use this work vector, to clean up, I just set this to 2. So now I've got a bunch of 0s and 1s here in my array, and this is an integer array. It's not a binary array. Okay. Then to clean up, I just increment the mark. And now I'm back to the assertion that everything in the array is less than the mark value. I cheated. And you just keep going. You use it again. You mark it by setting nodes to 2. Now your array has both 0s, 1s, and 2s in it. To clear it, you set this to 3. And now everything in the array is less than 3. And you go back to this assertion, this input assertion, that all the values are less than the mark value in constant time, rather than going through and clearing the work that you've done. That does not save asymptotic time, because you spent time to set these values to 2, and you could spend the same amount of time to set them back to 0, whatever. So it's not saving time asymptotically, but it's saving a constant time, which is important. The only thing you have to worry about is if you keep incrementing this from 3 to 4 to 5 to 6, on and on and on, what happens when integer overflow occurs? And I worry about those sorts of things. Okay? Then if integer overflow occurs, then suddenly it's easy to detect because the number becomes negative. If it's 2's complement arithmetic, that's easy to check. So you increment the mark value, and then you check it. And you say, well, are you negative? Which mathematically seems absurd, right? You're starting with a number that's 1, and you're adding to it, and then it becomes negative? Well, it's because you have integer overflow. And if that happens, then fine. You set this to 0, or you set this to 1, and then you go on the whole array, and you spend order n time to set it to 0. But the time you spend to do that is trivial, because you've just used the array 2 to the 32 times or 2 to the 64 times, depending on the size of your integer, which is a ginormous number. So asymptotically, if you think of an amortized complexity, the amortized complexity of then going back over this array and setting it to 0 is trivial. Okay, so there's lots of ways of improving how we use this W array. And I'll use this mark idea in the next code. The next code is real. This is executable code. This code really works. But it has, the core problem to this code is it's recursive right here. DFSR, R for recursive, is calling DFSR. So that's the killer. We've got to get rid of the recursion. This W array, we can improve its time complexity a little bit by taking advantage of this mark thing. In the next code, I'm going to then do both. I'm going to use this trick with the mark vector, and we're going to get rid of recursion. Now, taking a recursive code and making a non-recursive version of the same algorithm, iterative version, okay, is you've seen it already. I mean, you saw it with the triangular solve, the dense case. We had head and tail recursion, right? It just turns into a loop. But this is not that case. This is a depth first search. It's not going to turn into a loop. But converting a recursive pseudocode into a non-recursive iterative implementation is not that hard to do. The compiler does it for us all the time. Anyway, right? I mean, these are mechanics of what a computer scientist is adept at. So there we go. I don't have to talk about it there. Oops, there's the code on the next two slides. And there you go. Isn't that obvious? We're done. No, it's not obvious. All right? It's not obvious. I only have 3 minutes, so I'm not going to obviously talk about the whole algorithm. But I am going to talk about this this mark array. Actually, in this mark array, I chose to do something slightly different. I chose to have no separate mark array at all. So rather than saving time, I'm going to eliminate memory usage. Okay, so this is, you'll see in the code, you'll see other places where I use this trick here of marking the nodes and then setting a flag. But I have another trick up my sleeve which I'll use instead. Okay, and this trick will not save time because I'll still have to go back over the mark array and clear the marks. But it will save is memory. It will go away. 0. I will use 0 memory for this mark array. No memory at all. That's pretty good, isn't it? Go from size n workspace to no workspace. We'll have other workspaces for other things. Okay. But 0 workspace. And here's the trick. And it's done by these, it's rather obscure, so it's done by several macros. These macros, basically, think of it this way. The flip and the unflip are sort of like setting a value to -1 and then taking the absolute value. Suppose you've got an array and all of the numbers are greater than 0. But this value 5 in here, you don't want to lose the fact that this is equal to 5. That has some importance. So you can't just set it to 0 to do, to mark it or something. But there's that one bit that you're not using. It's a sign bit. If you know that all the values in the array are positive, and they carry important information, these integers. So you can't get rid of this information. But there's one bit you're not using. I can set that to -5 to denote the fact that two pieces of information. One, if W of j is negative, that means now it's marked. But I haven't lost the original data. If I need the 5, I just take the absolute value. Okay, so I'm using, if you will, I still have an order n workspace. It's now binary. And I'm using the sign bits of another vector for which I know always has to be positive. Well, what vector do we have that we know is positive? And it's of size n. The column pointers of our input data, our graph, right? Our AP array, they're all positive. They're all greater than 0. Oh, but 1. The first one is 0. So they're all greater than or equal to 0. So I can't quite use the sign bit because there's no such thing as a -0. So I've got to tweak this just a little bit so that I can have a representation of -0. And so I do a ones, it's kind of like a ones complement, but it's a little different. So that's what this is. That's what these 4 macros will do. So I'll explain what these 4 macros do. Once you see these macros, then you just have to say, oh, it's marked, it's unmarked, and we can just go on from there. And here's the unmarking, the restoration that has to be done at the end. This is the non-recursive part where it hasn't changed much. It just iterates across all the nodes in B and does the DFS. The next slide is the recursive part. But anyway, so I'll pick up here next class. See you then. Thank you.